with us. This is a kind of, our blessing for us actually. Yeah. Thanks a lot for your time again. Normally during this time you pick up your children here from school. Then at the moment you are sitting in your office, still in your office, just to give share with us. It is really, blessing for us. Thank you so much for your kind time and your effort for us. Yeah. I think without further ado, I will give back to Dr. Zakiuddin for Professor Lydia Wong to give her presentation. Yeah, thank you so much.
Okay, thank you very much, Prof. Herman, for the nice speech. And now we will give this opportunity to Prof. Lydia Wong to prepare the presentation. And this lecture will be held around 2 hours. Where around probably 1 hour of presentation, and then the rest will be a Q&A session. Prof. Lydia, the screen is now yours.
Okay, thank you very much. Good afternoon to Prof. Herman, and thank you all to all the students and staff who have already give your time to listen to this talk. And I'm always very happy to accept the invitation from UI to give a talk. If it's not because of COVID, I think I will probably have already spent a few weeks in UI last year, right? But unfortunately, COVID happened, and now we can only meet through the computer screen. But as I said, it's always my pleasure. So, and it's happened to be the right time. Now NTU is in the middle of exam. So now for me, this is the calm before the storm. Next week after exam, I will have to mark the exam papers. So the timing is really good. So I'm also happy to accept this invitation. Yeah. Okay. So today I will share with you an introduction topic of solar cell materials. Are you able to see my screen?
Yes, it is
Yes,
visible.
Okay.
yes,
Okay. Okay. Let
already.
me just make it full screen. Okay. So all right, so as I learned from Prof. Herman that the majority of the students here are second year students, right? Semester 4, yeah. And this is probably the first time you have heard about solar cell materials or solar cell in general. I mean, you may have heard about solar cell, but how does it work? The principle behind this is probably the first time you encounter this. So I will spend some time to discuss this before I go into the different types of materials used in solar cell. So this is the outline of today's talk. I will explain the basic principle of photovoltaic materials, and then the material selection principle of photovoltaic materials. And then in the second part, after we take a short break, we can discuss in a little bit more on the different types of solar cells, the 3 generations of solar cells, including silicon, thin film, organic PV, dye sensitized, and also perovskite. Now, this topic is actually in NTU. It's offered as a prescribed elective in the 4th year. And I spent around 5 to 6 weeks or close to 10 hours, 10 to 12 hours of lecture time to cover all of this in greater details. So what I'm giving you now is just a flavor, it's just a teaser on the actual content. So if perhaps if you have the opportunity to come to NTU for exchange, then you will get to experience the full course. Yeah, this is just a sample course. But if you come to NTU, you can experience the full course. Actually, in the past, we hosted exchange students from UI. So I hope now with a lot of initiative from the Mendikbud, there will be more funding for Indonesian students to go overseas for exchange. Yeah, and NTU, I know NTU always have an open door policy for UI students. So it depends or not whether the UI students want to come and whether or not the border is open. Okay, all right. So now I will start with this. I'm sure I don't need to convince you that the threat of global warming is real, right? Actually, it's very easy. Jakarta is getting hotter, right? So the problem with global warming is the melting of the ice in the northern and the southern Atlantic, and the worst thing that can happen is if the Earth temperature keep increasing by 5 degrees C at the year of 2100, the sea level will increase, and because of this, Jakarta, Singapore, and Beijing will disappear. It will all be flooded. Yeah. So you also notice and you experience yourself how flooding in Jakarta will basically make the whole city shut down. If we don't prevent global warming, we all will live like an Aquaman in 2100. Yeah. Okay. So in order for us to reduce global warming, we need to reduce carbon dioxide emission. And the largest carbon dioxide emission or CO2 emission is coming from the emission of vehicles, yeah, as well as the emission from the industry. And this is because we are always using the fuel which generate a lot of CO2. The coal or the oil that we burn generate a lot of CO2 and causing a global warming. So one way to prevent the generation of CO2 is to use a renewable energy, and solar cell is one of the best candidate, cleanest candidate to generate clean electricity. Why is that so? Okay, basically, the energy that is emitted by the sun is so huge that if you can harvest all of the energy generated in 1 hour, you can actually provide the energy demand of the whole world in 1 year. If just 1 hour of sunlight can power the whole world for 1 year. Or if you cover Sumatra, the whole island of Sumatra, with a 12% efficiency of solar cell, this is enough to deliver the entire world's energy demands. Okay, of course, this is not so easy because you need to have solar cell close to your the place where you want to use this electricity. Yeah, you cannot transfer the electricity wirelessly from Sumatra to North America, right? So of course, this is a simplicity, but this is the reason why a lot of people are trying to use solar. The potential is huge and it is readily available everywhere in the world. Okay, so the photovoltaic materials was first, the effect of photovoltaic is first discovered in the 1839 with the discovery of liquid this one is a liquid mercury by Edmund Becquerel. And then the effect of photovoltaic in solid is also discovered a few years later. And the first solid solar cell is actually shown in a selenium solar cell in 1883. Okay. And then in 1930, copper oxide solar cell is used. And then the first silicon solar cell is demonstrated in the 1940s. After the Second World War, the crystalline silicon solar cell in Bell Labs reached 6% efficiency. And in 1958, it is used as in the spaceship. Okay. And then after that, there are more and more materials coming up to also to, because the silicon solar cell efficiency, the maximum efficiency of silicon is around 20 to 30%. So many people are also trying to find alternatives. And then in the 2008, about 12 to 13 years ago, there's an oil crisis, and interest in solar cell research is getting a lot of attention again. Yeah. So you can see the first effect of photovoltaic is discovered in 1839. It's almost 200 years ago. And only now, almost 200 years later, we can see a lot of adoption for this technology in our real life, right? You can start seeing a lot of solar panels used on the rooftops. So you can see how long it takes from science, basic science, to applied science. Okay. So this is the Vanguard space shuttle, which used the first PV technology in 1958. It lasted 2 weeks with battery, and then use photovoltaic for the rest of the time. Yeah. So this is a very, very good breakthrough at that time. Now in NTU, if you happen to visit us, we have installed solar panels in all of the rooftops of NTU. This is the aerial look. If you take a drone or take an aeroplane on top of NTU, this is how it looks like. Okay. My office is probably somewhere here. Let me see if I got it correctly. But there is around 5 milliwatt solar panel installation in the whole of NTU. And this is the largest installation of solar panel in a single location in Singapore. Okay, so this is a demonstration. So NTU has become the living lab of Eco Campus, where we also conduct research to analyze the usage of solar panels. How can it actually replace electricity 100% without any break, for example? Yeah, and what is the energy efficiency? What is the cost saving, etc.? So our campus has become a living lab for solar panel installation. Now, what is a photovoltaic device, or what is a solar cell device? It is very easy. The basic component of a PV device, it only consists of 2 layers of semiconductors, P-type semiconductors and N-type semiconductors, sandwiched between positive metal electrode and negative metal electrode. Okay. Now, I hope you know what is semiconducting materials, right? If you don't know, you better quickly Google semiconducting materials, because I will ask you questions related to this later on. Yeah. So you need P-type semiconductor, N-type semiconductor sandwiched between 2 metal electrodes. And then one side must be transparent, because you want light to go in from one layer to be absorbed by the semiconductor's material. Okay. Now, what is the process of solar to electricity conversion process? A PV device, a photovoltaic device, absorbs and converts lights or photons into electricity or electrons by generating electron hole pairs. Okay, and these electron hole pairs will create a photo-induced current. So this is your photovoltaic materials. Okay, so once you shine light upon your photovoltaic materials, okay, basic semiconductors materials. What is the difference between semiconductors and metals? Can anyone give me an answer? Are they muted, or can they actually unmute themselves?
Yes, they can unmute themselves.
Okay, anyone wants to give an answer to this?
May I answer, Prof?
Sure.
Okay, so my name is Maurice, and my answer is like semiconductor basically have a conductivity between a ceramics and metal, in which they have a conductivity and insulator. Metals are usually more of a conductors, while ceramics is more like the insulator. So semiconductor is like in the middle between the two.
Wonderful. Very good. So now the next question is, what will make a semiconductor conducting? How can you make a semiconductor conducting? Okay, so if you recall, you know the concept of band gap, right? A semiconductor has a band gap, a valence band and a conduction band. Okay, maybe let me just share let me share a whiteboard. Can you see my whiteboard?
Yes, Prof. We can see your whiteboard.
So for semiconductor, the characteristic of a semiconductor material is there is a band gap, right? The band gap consists of a valence band. Valence band consists of all the bonded electron and the conduction band, which is empty states. So in order for semiconductor to conduct electricity, it needs external energy to excite electron from the valence band to the conduction band. When one electron is excited at the conduction band, then it will leave behind a hole. Okay, so this energy, the external energy, can be heat, it can also be light or photons. Okay, so once one photon is absorbed, it generates one electron and one holes. The electron in the conduction band become the free electron, which is called a photon-induced current. This is how solar cell absorb photons and generate a lot of free electrons in the conduction band and produce electricity. Okay, is it clear? So you need a semiconductor because you only want this to conduct to generate these free electrons when you shine photons on it. All right, okay. So I will come back to my slides. Okay, so what happens during this process of photon to electron conversion? The first thing that happens is light is being absorbed, and when light is being absorbed, electron and holes are generated. As I mentioned, this is electron, holes, and then the next step is charge separation. You want to filter the electron from the holes. You want to separate them. You want one electron to go one side and one hole to go to the other side. And this charge separation happens at this p-n junction. Okay, so once you separate them, and then you collect electron on n-type side, and you collect holes in the p-type side. Okay, now before I move on, before I confuse you further, who can tell me what is p-type semiconductor and what is n-type semiconductor?
Don't be shy, please.
Have they learned this before?
Yeah,
Prof?
of course. Yeah.
See, now no excuse. If you are shy, you can chat.
They already study in the first semester actually for the engineering materials.
I see.
Subject, yeah.
So usually in NTU, the student will return all the knowledge to the professor after exam. So maybe this is the same case, huh? Anyway, p-type semiconductor means the majority of the carrier is holes. The n-type semiconductor means the majority of the carrier is electrons. Yeah, so p-type means hole rich, n-type means electron rich. Okay. All right, so I will move on now. Okay, so this is what I mentioned just now, right? Photons is being absorbed in the semiconductor in the p-type and n-type, and then electron will go to the conduction band, holes will remain in the valence band, and holes will move on to the p-type, electron will move to the n-type. Now, what makes an efficient solar cell? An efficient solar cell is a solar cell that can produce as much electricity as possible, right? And this means you need to generate as much electron as possible. Okay, and how can you do that? Is actually by optimizing these two processes. You need to optimize, you need to absorb as much photons as possible. You need to absorb as much light as possible. And after you absorb as much light as possible, right? In other words, you generate a lot of electron and holes in the conduction and in the conduction and valence band. You need to make sure that this electron and holes can move to both sides of the electrons as much as possible. If along the way, these electron and holes meet with impurity, they can also recombine. Their lifetime will be short. Then you will lose the electrons because the final current, the final power that you generate from this solar cell only accounts for the electron and holes that can reach the metal electrode. Okay, so you need to absorb as much as possible and make sure the electron and holes can travel safely. Okay, and this is the job of a materials engineers. How can you design a materials that can absorb as much as possible, but also transfer electron and holes as much as possible? Both to satisfy these two conditions are not easy. Material that can absorb light, there are a lot of materials that can absorb light, yeah. But materials that can absorb light and conduct electricity well, there are not too many. Okay. Any questions up to this point?
Not yet, Prof.
Not yet. Okay, good, very good. Okay, so now the next question is, you have this periodic table, right? How can you choose a materials to be a good solar cell material? Which element is good as a solar cell material? What is the guiding principle, right? To choose which one, or you just take a dot and then throw in the periodic table, which when your dot where your dot lands, that will be the solar cell materials. It cannot be, right? You have to choose something, and you need to have a principle to choose. So let's do an interactive survey. Yeah, please scan this QR code. Okay, or you can also type in this this address in your laptop. You can use laptop or you can use mobile phone. And then you can start participating in the quiz. Yeah, this is the question. Are you able to see the question? I already switch it on. So the quiz, the question is simple. Which of the following elements is not used in solar cell? I give you 8. One of these is not used in solar cell. Okay, I see someone is, okay, more people are responding. Very good. Are you able to access the site? Do you have problems? I see 8 people or 9.
Maybe
9.
they are still accessing.
Okay, okay. We'll wait.
Yeah.
So this is an example of my class in NTU. I will usually give them questions, and for some courses, I will mark their answers. So they cannot skip class. If they want to earn their grades, they have to attend. And And for some classes, I actually posted the lecture notes and lecture video before the live lecture. They have to study first. And during the live lecture, I will give them questions and they will be marked. So many people complain because they cannot skip class anymore. They cannot do a sistem kebut semalam sebelum exam. But the good thing is, after I force them to do this, I think their understanding is better because the questions they ask me before exam is much, much better. So the moral of the story is never do SKS, sistem kebut semalam. Yeah, I think Prof. Herman agree with me lah, but the students may not agree with me.
Indeed.
Okay, I see more people are coming in. I can still wait. Yeah, which of the following elements is not used in solar cell? Let me see. Interesting. Actually, every element have someone voting for it. Okay, maybe not to waste too much time, let me just show you the answer. I share my screen. Can you see my screen now? The question screen?
Yes, Prof, we can see.
Oh, sorry. Okay, you can see the question, right? Which of the element is not used in solar cell? Okay, so I will show this. Okay, you see? Wow, interesting. Interesting. You can see how many people voted for each element, right? And then there are also 3 of you who are confused. Okay. Okay. I'm not going to give you the answer now. Okay, I can give you the answer, but I will not explain. Actually, only one element is not used in solar cell. And the right answer is uranium. Okay, this is usually used for nuclear reactor. But all of the other elements are used in one way or another. Okay, including hydrogen, including chlorine, including silver. Yeah. So now I want you to pay attention to my lecture because at the end of this lecture, I will reveal which element is used in which solar cell. Okay. All right, good. Okay, how can I stop this? I think I can just, okay, I can just continue to the next slide. All right. Can you see my PPT now, my PowerPoint?
Yes, Prof, we can see your.
Okay, good. Oh, okay, good. Now, we come back to the factors affecting absorption. Yeah. So the first factors that affect, so this is how you select your materials. If you remember the first thing that happened when a material absorbs, the first thing from the that happens during photon to electron conversion is absorption of light. So the material you choose must be those that can absorb very well. Okay, and this depends on the band gap of the materials itself, the band gap of the semiconductor. Yeah, and light absorption can only happen if the band gap of the material is smaller than the energy of the photons that is absorbed. Okay, the smaller the band gap, the more photons can be absorbed. Okay, so let me further elaborate this. So this is the schematic of a semiconductor. You have a conduction band and valence band. And this semiconductor has a certain band gap. The band gap is the distance between the valence band and the conduction band, the energy difference between the valence band and conduction band. So if the energy of the photons or the incoming light is smaller than the band gap, what will happen is it becomes, the photons will pass through as if this material is transparent. if the energy of the photon is equal to the band gap of the semiconductor, it will have enough energy to excite electron from the valence band to the conduction band and generating the free electrons. Now, if you have, if the energy of the photon is much larger than the band gap, it can generate electron to the conduction band, but it will be excited because it energy is conserved, right? What you absorb, what the incoming energy will be, the same energy will be absorbed, but because the band gap is smaller than the photon energy, there is an excess energy, extra energy, which is released as heat. Okay. Are you able to see my cursor, my mouse?
Yes, Prof. We can see your
Okay,
mouse.
good, good. Okay, good. Okay, so the energy of the photons can be correlated with the wavelength of light. Yeah, the energy of the photon is correlated with the wavelength of light using this equation, where h is the Planck's constant and c is the speed of light. Okay, so knowing this equation, you can take a look at the solar spectra. This is the solar spectra. What is the solar spectra? Imagine you have a spectrometer, okay? You put this spectrometer directly under the sun and you measure the graph. This is the graph that you will obtain. It will have a wavelength. On the x-axis is the wavelength of the light, and then on the y-axis is the irradiance, or the power generated per unit area, how much photons generated per unit area. So this is the spectra of the sun. All right. If you can see, this is the visible range of light, right? Between 400 to around 800. This is the region with the most number of photons. The higher the curve, the higher the number of photons. So if you can design your solar cell in such a way that you can absorb most efficiently within this 400 to 800, then you will optimize the solar cell absorption. Okay. Beyond this, for example, beyond 1000 degrees C, these are what we call as infrared, or usually this is heat. Yeah. So some of the coating on the windows are actually reflecting IR out. So when photon or when light come to your window, the infrared portion will be reflected out so that heat doesn't come into the room. Yeah. But for solar cell, what you want is optimum absorption in this visible region. Now, just now I mentioned that this wavelength, right? This is the wavelength of light. This wavelength can be converted into energy of photons. So we can actually replot this graph into another graph, which is like this. And on the x-axis, instead of wavelength, we have a energy, semiconductor band gap. Okay, and this is the band gap of some of the popular semiconductor used as solar cell. Amorphous silicon, this is amorphous silicon here. Maybe I annotate. This is amorphous silicon. This is gallium arsenide. And this is, this is silicon. This is the band gap. Okay, now, can you go to your WooClap again? This is the next question. Based on the band gap, right? Sort the following solar cell from the highest to the lowest efficiency. Are you able to see the question in WooClap?
Yes, Prof. We're able to see that.
Okay, so I will keep my slides on the band gap, and then you can look at your screen on your phone to answer my question. Sort the following solar cell from the highest to the lowest efficiency based on the band gap. See whether you understand the concept I told you earlier. So just to remind you, right? The condition for absorption is the band gap should be smaller than the energy of the photons. So in this case, amorphous silicon has a band gap of 1.5 eV. Yeah. Gallium arsenide has a band gap of, let's say, 1.4 eV. Silicon has a band gap of around 1.1 eV. Okay. So amorphous silicon is the highest band gap. Silicon is the lowest band gap. Which one will absorb the most? Which one will have the highest power conversion efficiency based on the band gap? Is the question clear? Do you need me to explain again?
No, Prof. It was really clear.
Okay. So what you need to ask yourself is the following. Is a lower band gap solar cell absorb more or less? The lower the band gap, does it absorb more or less? Okay, I can. So you know the smallest band gap is silicon, yeah? The highest band gap is amorphous silicon. Okay, let's take a look what is the, wow, interesting. Interesting answer. Okay. Okay, let me share. Okay, can you see your result? So winner is gallium arsenide, the highest efficiency, amorphous silicon and crystalline silicon. Second, these two are even. Crystalline silicon, gallium arsenide, amorphous silicon. Okay. Interesting. Okay. Let me ask you a question then. If the band gap is smaller, right? Will it absorb more or less light? You can maybe write in the chat more or less.
It will absorb more if the higher band gap is available. Thus, if amorphous silicon has around 1.5 EV, it will have more absorption to light.
Okay, so in other words, amorphous silicon is 1.5. Silicon is 1.1. Which one absorb more?
Amorphous silicon.
Okay. All right. Very good. This is why I posed this question. Okay, let me show you my PPT again. Okay, so the smaller the band gap, right? That means there are more photon with higher energy that can be absorbed, right? So the smaller the band gap, the possibility of photons with higher energy that arrives on it can be absorbed. So the smaller the band gap, the more photons can be absorbed. So if you look at this, right? Amorphous silicon can only absorb light that is shaded here. Light photons with energy larger than the band gap, which is larger than 1.5, can be absorbed. So only this part can be absorbed. Gallium arsenide can only absorb this part, anything that is larger. Silicon absorb this much. Okay, so you want to change your answer? Okay, actually cannot change anymore, but the majority of you guessed correctly. 12 of you guessed the correct sequence: silicon, gallium arsenide, then amorphous silicon based on the band gap. Yeah. However, in reality, right, I want to ask those who actually, I don't think so. Okay, in reality, gallium arsenide is the highest efficiency compared to these three in reality. Why? Amazing, right? The gallium arsenide band gap is actually larger than silicon. Okay, why does it have higher efficiency than silicon? The reason is there is another parameter, another factor that affects absorption. Okay, and this parameter is absorption coefficient. What does absorption coefficient mean? This means how much photons can be absorbed per unit length. Okay, example is in this graph. So this graph is the absorption coefficient of a material on the y-axis as a function of wavelength. Okay, and the colorful lines represent different types of solar cell. Okay, so the purple line here are the germanium, is the germanium. Crystalline silicon is the red color here. Amorphous silicon is the pink color, and gallium arsenide is yellow. Okay, so how do we understand this curve? Let's take a look at 600 nanometer wavelength. At this wavelength, okay, silicon can only absorb this much of electron. Amorphous silicon can absorb more. Gallium arsenide can absorb even higher. Okay, so the area under this curve that falls within the visible range of solar spectra, right, will be the most efficient to absorb. If you remember the solar spectra just now, if you remember the solar spectra just now, the shape is something like this. This is the solar spectra. This is what the sun emits. So you see the peak is in this region. So you can see that if you can absorb as much photon as possible within this range, you are absorbing the most from the sun. Okay, and because gallium arsenide has a higher absorption coefficient compared to these two, it actually has a higher efficiency than amorphous silicon and crystalline silicon. Of course, there's another factor. Gallium arsenide has a very good electron and hole mobility. That's why the transport of the electron and holes are also much more efficient compared to silicon and amorphous silicon. Okay, any questions up to this point?
Yeah. I'm sorry, may I ask a question?
Sure.
What is the parameter to, I'm sorry, the absorption coefficient? What's parameter to calculate the absorption coefficient? How we calculate absorption coefficient in each material? Thank you.
Okay, good. So that is in my next slide. Okay. Let me just erase this. What is the definition of absorption coefficient? So absorption coefficient measures how much photon is absorbed per unit length, right? So for example, if this graph represents your material and x equals to 0 represents the surface of your material, when light is being absorbed, light comes from the surface, the intensity of light that is absorbed on the surface will be the highest, correct? As the photon is absorbed deeper into the material, the intensity will drop. And this drop in intensity follows this relationship, which is exponentially decreasing. So the intensity as a function of x, as a function of depth inside into the material, decay exponentially. I naught is the original intensity on the surface, and then there's a Gaussian function exponentially dropping, okay? And the constant, the exponential constant here, alpha, represent the absorption coefficient, okay? Now, this is usually measured. You can measure this by UV visible spectrometry. I'm sure Prof. Herman has this equipment in the lab. So if you want, you can try. So you can basically measure the absorption coefficient of different types of material. And this is actually a constant. So once you measure, as long as you did it properly, you can use this number again and again. It will be correct. Yeah. And the absorption coefficient number for different types of material, for material that is usually used in solar cell, is already summarized in this graph. Okay. All right. I hope I answer your question. Okay. So actually, the absorption coefficient can be used to measure, to determine the absorption depth of light. So for example, the first thing you need to do when you select the materials is the band gap, right? Once you identify a material with a low band gap, the lowest band gap possible, the next thing you need to ask yourself is whether this material absorbs light well or not. Yeah, and this depends on the absorption coefficient, and this will translate to how thick your solar cell will be, the thickness of your solar cell. And the thickness of your solar cell is inversely proportional to the absorption coefficient, which means if your absorption coefficient is high, the thickness of your solar cell will be less. You need to use less material if the absorption coefficient is high. Okay, so this is another design parameters in solar cell. Okay, any questions? Okay, I think there's no question. Okay, so just to recap what we have learned so far about light absorption. First, the band gap of semiconductor should be smaller than the photon energy. So the lower the band gap, the better. And then the semiconductor thickness must be higher than the absorption depth or the absorption thickness here. So once you calculated how much is your absorption thickness, then you can determine how much is your semiconductor thickness. Okay. And the last criteria is minimum shading by the positive electrode. What do I mean by this? The top electrode is made of metals, right? And metals are usually shiny and absorb a lot of light, but it will not, because it absorbs too much, this light will not go through to the semiconductors. So in order for the lights to go to the semiconductors, you need to make sure that one side of these electrodes are made of fingers instead of a uniform thin film. Okay, so the less shading you have, the better will be, the more lights will be transmitted into silicon. Okay, minimum shading by the positive electrode. Okay, let me just move to get a piece of solar cell. Okay, so this is an example of a solar cell. Can you see? And these lines that you see here, these are the electrodes. In silicon solar cell, it is made of silver, right? And this is very thin. The black ones are actually silicon. Okay, so you cannot cover the whole region of silicon solar cell with silver, because silver will just absorb everything and you will not be getting electricity from the light. Okay, is this clear? Any questions? Okay, so I think this is the last slide before we have a short break. All right, how do you measure a power conversion efficiency of a solar cell? So when we talk about solar cell, people always say, okay, silicon has 20% efficiency, gallium arsenide has 30% efficiency. What does it mean? Okay, power conversion efficiency of a solar cell is the ratio between the output power that is generated of the solar cell in relative to the incoming power. So how much electricity is generated out compared to how much photon is being supplied into the solar cell. How much light you shine onto your solar cell. And you can measure this using an IV meter, right? This is Kifli. Usually in your lab, you should have this. In electrical lab, you should have this. And the behavior of a solar cell is very similar to a diode, PN junction. So if you measure this solar cell, right? If you measure this solar cell in the dark, no light at all, and you measure the current I versus voltage, what you will get is this dotted line. This is the IV curve, yeah? And then you switch on light onto the solar cell and you measure again what is the current and the voltage. What you will get is the right curve over here, okay? And the important parameters of this solar cell are the open circuit voltage, short circuit current, and the squareness of this curve, which is the fill factor. The more squarish this curve is, the higher is your fill factor, the higher your short circuit current and open circuit voltage, the higher will be your power conversion efficiency. Okay, so I am not going into too much details on this because I will need another 2 hours to explain this properly. But I just want to introduce to you what is the power conversion efficiency. Okay. All right. Any questions up to this point? Otherwise, maybe we can have a 5 minutes break. You can either go to the toilet or you can stretch yourself.
Yeah, agree, Bu Lydia.
Okay, all right. And then I will try to check the chat. Okay. If there's any question on the chat.
Miss Lydia, if I may ask a question?
Sure.
From your explanation that one of the problem is how we minimize the shading from the PV ribbon, from the aluminium. So how can we decrease the shading of the PV ribbon itself? And we decrease the shading, but also we do not disturb the resistance or other physical properties. Thank you.
Very good question. And actually it's a long answer, right? Let me try to give you a short answer. There are a lot of clever ways to do this. The first generation of solar cell, probably you will have huge, so that you can control the area, the width of each of these metal lines. And as the technology advances, this width is getting smaller and smaller. So that is minimizing the shading. However, there is a negative effect to this. When you have less electrode, you collect less electron. So your power conversion efficiency actually drops. So there is a trade-off. So how people circumvent this problem is they dig inside silicon, make a buried junction. So maybe let me see whether I have the picture here. Yes. Can you see my screen? Yeah. Imagine if you only have so this is the lines, right? This is the metal lines. Initially, you have very thin layers like this. So the only these lines are able to collect all your charges. But now what you can do is you can dig deeper into silicon and collect more charges from the walls of this buried electrode. So in this case, you still have the same amount of shading, but you also collect more electrons. Okay, actually there's a lot of discussion on this. Okay, but that's my short answer. Okay.
Thank you very much.
All right. Okay, there is a question in the chat. What are the physical characteristics that easily observable of high absorption materials? Can anyone guess? If a material absorbs light, that means the photons are being absorbed, right? So the more opaque your material, the better it is. The less transparent your material, the more absorbing it is. So glass, for example, glass is transparent, right? See-through. This one is low absorption. Then you compare with carbon, black. This is very high absorption. Okay. All right, I think it's more than 5 minutes. Maybe I should get started again. Okay. All right, so based on the materials, right, we can classify solar cell into 3 generations. The first generation of solar cells use crystalline silicon. It is usually bulky. Has anyone of you seen a real solar panels made of silicon? Has anyone seen a real solar? Those who have seen, right, you can probably raise your hand in the Zoom. 1, 2. Only 2 of you.
I think they are too shy, Prof. Lydia.
Too shy.
Too shy, yeah. Ayo.
I don't even see your face, right? You're so far away. I cannot even touch you.
I'm very sure that they already see somewhere. Yeah, if they don't have at home, of course they can see somewhere, even in our campus already.
Oh,
In Faculty of Engineering, actually, we have installed in our new integrated teaching laboratory, and also in the Danau, yeah, UI Danau Lake, yeah. Actually, some protecting solar cell.
So those who have not seen, right, it's time for you to go around the campus, go walk around the campus. Maybe it's too long. You have not been in campus for too long already.
That's the answer.
Okay, has anyone tried to carry a solar panel? The real solar panel. Actually, to be honest, I also never try. Because why? One solar panel is 25 kilogram.
Yeah, you are right. Yeah.
25 kilogram. Imagine if you go overseas, right? One luggage, one of your copper, right, is 20 kilo. That one is very heavy. You imagine one panel is 25 kilogram. That's how heavy is a solar cell, a silicon solar panel. That's silicon solar cell. The silicon itself is very thin, but the encapsulation materials, the substrate is very heavy. So because of this, it limits the application. You can only see silicon solar cell on the rooftops, and also your rooftop must be very strong. Yeah, if your rooftop is made of jerami, cannot, right? If your rooftop is made of wood, probably it's not strong enough to carry your solar panels. So because of this, the usage of silicon solar cell is limited. So that's why, that's why people move to the second generation of solar cell. In the second generation of solar cell, they use thinner materials. So for example, the solar cells that I have now, this is made of CIGS solar cell, copper, indium, gallium, sulfide, selenide. This is extremely thin, and you can deposit this on a plastic or a stainless steel, and it is very lightweight. It's also flexible. So imagine if you want to install this on the window. You can actually just stick this to your window or to the side wall of the buildings. You can also bring this to outer space. Yeah, because if you carry silicon, you need to build your spaceship with a strong enough structure to carry solar panels, silicon solar panels. But with this, you don't need to have a very strong support. Okay, this is the reason why people go to the second generation solar cell, and also third generation of solar cell. The third generation of solar cell use organic materials. Organic materials means those material with high carbon content. So for example, polymers, small molecules, these are all organic materials, and nanomaterials. Yeah. And there are different types of materials that you can use in the second and third generation of solar cell. So now I will go through very quickly different types of solar cell for each generation. The first generation is silicon solar cell. Okay, okay. This is, if you cut the silicon solar cell, this is roughly the structure that you will get. On the bottom, you have an aluminum surface with a contact. The bulk of the material is silicon, P-type and N-type. And then the top part is actually anti-reflection coating. And then the metal lines that you see here, usually they use silver electrode. Yeah. So this is how crystalline silicon look like. And as I mentioned, the benefit of crystalline silicon is it is very stable. Do you know what is the warranty given for silicon solar cell? Let's say you buy a silicon solar cell, install it on your rooftop. How long will it last? 5 years, 10 years, 20 years, 30 years? Somebody mentioned 25 years in the chat. Any other guess? I give you option. 5, 10, 15, 20, 25. Wow, 25. Okay, wow, very high, yeah? You sure? Okay, actually, you are right. The warranty usually is at least 20 years. So silicon solar panels can last for 20 or even more years. So this is the good thing. The cost of installation is high. So at the beginning, it's a high installation cost, but as you can actually install it for 20 years, after a few years, you will break even. So I did the calculation with my students in Singapore. So we compare the cost of electricity generated by solar panels for one household, compare it with the price of electricity that we use from our PLN, yeah. And the numbers, can you guess how many years it takes for Singapore house to break even? Any guess? How many years will they break even? 6 years, somebody says 6 years. 5 years, maybe 2. Okay, not bad, not a bad guess, not a bad guess. Okay, actually, our calculation shows that the range is between 4 to 8 years. 4 to 8 years, you can break even already. If we stay in a landed house, imagine if it's a landed house, yeah, just like the housing in Jakarta or Indonesia, 4 to 8 years can break even. So after 8 years, you pay $0 for electricity. But unfortunately, in Singapore, if you have visited Singapore, we have very little land, right? So most of us live in apartment. It's a very high density living. And even if we cover all the rooftop in Singapore with solar panels, we will not be able to replace electricity. It's not enough. The power conversion efficiency is not enough. Yeah. So for this reason, the research for solar cell is still open. Can we actually find a material that is much more efficient than silicon, as stable as silicon, as cheap as silicon? Efficient, cheap, stable. This is the keywords. But again, it's not simple. A material that can fulfill these 3 criteria is very few. Yeah. So the next type of material is called amorphous silicon solar cell. This is made of amorphous silicon. The absorption coefficient is higher than crystalline silicon. And because of that, amorphous silicon can also be made very thin. It can be made into a flexible solar cell. Yeah. The problem is the efficiency is low. The highest efficiency is probably around 10%, and it is not very stable. Can you tell me an example of application that use this amorphous silicon? Actually, you may have it, Can you make a guess? See, Prof. Herman give a clue already. So actually, your watch, some of the watch is solar battery, right? This is usually using amorphous silicon. Your calculator, those with the solar panels on it, those also amorphous silicon. But this is cheap and good, can power small, low power material, low power devices, but not for big housing. Yeah. Okay. So this is amorphous silicon. The next one is polysilicon thin film solar cell. This is also another type of silicon. It has better absorption coefficient, so you can also make it into a thin film. Okay. And polycrystalline has a lot of grain boundaries, yeah, compared to crystalline silicon. Okay. But within the grain, the band structure and absorption coefficient is similar to single crystal silicon. Okay. Okay, now I think, can you go to your vocab again? I've told you about crystalline silicon, amorphous silicon, and polycrystalline silicon. All three can be made into silicon solar cell, into solar cell. Now, what is the main difference? Actually, there can be more than one answer here. There can be more than one correct answer. What is the main difference between crystalline, amorphous, and polycrystalline silicon solar cells? Okay, let me share your answer. Okay, can you see the answer now? All right, wonderful. Okay. What are the main difference between crystalline, amorphous, and polycrystalline silicon? So you all materials science students, right? You know what's the difference between amorphous, crystalline, and polycrystalline, right? So the main difference is in the morphology. Amorphous is a random structure. Crystalline is very regular, very aligned crystal lattice. Polycrystalline has a lot of grain boundaries. How does this affect the optical and electrical characteristic of this material? Okay. Now, the band gap is affected. Yeah, amorphous material absorb more. Absorption coefficient is affected. Amorphous material absorb more. So it is higher for amorphous compared to crystalline silicon. The band gap is also somehow affected, right? If you remember the previous slides, amorphous silicon has 1.5 EV band gap, silicon has a 1.1 EV band gap. So it is also affected. Doping, how about doping? Actually, the dopants material that we use to make p-type silicon, p-type amorphous, or p-type polycrystalline are the same. So the doping is the same. So doping is wrong. Now, actually, the main difference between these three, if you can only choose one, right? The correct answer is electron hole mobility or lifetime. Why is that so? Can anyone guess? Actually, if you can only choose one, yeah, number 4 is the correct answer. This is the greatest difference. The band gap changed from 1.1 to 1.5 EV, not much change. It's not like 1.1 to 4 or 5 EV. The color is still black, so it's not much difference. Absorption coefficient changed one order of magnitude, 10 to the power 4 to 10 to the power 5 at 3. 10 to the power 3 to 10 to the power 4. But electron hole and mobility can change a lot. Why? Any guess?
May I guess? Prof?
Sure.
So if you're talking about crystalline or the amorphous materials, it strongly corresponds to the atomic arrangement of the material itself. So if we connect it to the electron mobility, it will be affected, for example, in less ordered materials, which is the amorphous materials. I think it will be very much difficult for electron to move or within the material.
Very good. Very good. So basically, if you have one material which is amorphous, right? This is amorphous. This is polycrystalline. Within the polycrystalline, it is crystalline. And then this is a perfect crystal. The electron mobility will, from amorphous to crystalline, will increase. This will be the highest. This will be the lowest. And electron mobility is related to the lifetime of electron. Meaning, how long does it take for this electron to recombine with holes? So because of this one has the best transport properties compared to this amorphous. Okay, so this is the challenge. I don't have time to talk about this, but this is usually the problem with most of the new materials for solar cell. You can find materials that absorb light, but can this material transport electron and holes efficiently? Very few can do this. So if you see a lot of publication, oh, I can find this material, that material can absorb light, can generate electricity. Yes, sure. Probably your efficiency 1%, 5% is not good enough. You need to have at least as good as silicon, 20%. Then you can compete with silicon. Okay. Okay. So now I move back to my slides. Okay. Okay, so the next type of thin film solar cell is made of cadmium telluride materials. Okay, this is the structure of a cadmium telluride, cadmium sulfide solar cell. It starts with a substrate, right? Or this is the inverted structure. So the glass is on top, and then you have a cadmium sulfide as an N-type material, and cadmium telluride as the P-type material. So in our previous discussion, when we discussed about silicon, the P-type and N-type material are all silicon. You just dope differently. One using boron, the other one using phosphorus, then you get for a P-type and N-type semicon. In thin film solar cell, from this point onwards, usually the P-type and N-type material are two different materials. Yeah, so they may have different band gap, and they may have different crystal structure. Yeah, so this creates more complexity. Okay, the reason is because most materials are difficult to dope. Silicon is very unique because silicon, you can change the majority carrier by doping with boron or phosphorus, right? All of the other material, they like to be P-type or they like to be N-type. They don't like to be both. Yeah. So the first layer is cadmium sulfide. Okay. I don't have time to go through so much details on this. The second layer is the cadmium telluride. Okay. This is the main absorber. And also you have the back contact. Okay. This material is actually very good. The efficiency of cadmium telluride is more than 20%. It is already commercialized. One of the, actually the biggest manufacturer of cadmium telluride based solar cell is in US. It is called First Solar, and they have a manufacturing facility in Malaysia. Yeah, so cadmium telluride solar cell is manufactured in US and also in Malaysia. The problem with this is they are actually, okay, these are all too details. Let me just show you this slide. The main problem with this, can you tell me, if you look at the materials we use to make cadmium telluride and cadmium sulfide solar cell, what is the main concern for this material? Can you guess?
Is it toxicity, Miss?
Toxicity. Which material is toxic? Which element is toxic?
Cadmium.
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 Cadmium is toxic. Yeah, cadmium is toxic, and because cadmium is toxic, it is banned in Japan. Japan doesn't allow solar cell with any material with cadmium. They don't allow production in Japan. So I will tell you another stories later. So Japan banned this. Europe also is not keen. That's why they can only manufacture in Malaysia. So if Indonesia wants to have a solar cell manufacturer, maybe you can bid for this lah, right? We have a lot of islands. You can have a remote solar cell manufacturer somewhere. Yeah. Okay. The next thin film solar cell is CIGS solar cell. This is made of, oh, I didn't put the abbreviation here. CIGS stands for copper, indium, gallium sulfide solar cell. Okay, this is the structure of the solar cell. It consists of a transparent conducting oxide, N-type cadmium sulfide, as well as CIGS. Now, Japan has the highest efficiency CIGS manufacturer in the world, Solar Frontier, but because cadmium is banned in Japan, they use different type of N-type material. Okay. All right. So the efficiency of this solar cell is also high, 22%. So this is also competitive with silicon. And this company, which produced the highest efficiency and also manufactured this technology, is Solar Frontier, a Japanese company. The problem is it is not easy to produce a large numbers of CIGS because this involve 4 elements: copper, indium, gallium sulfide. So to control the uniformity of these 4 elements on a huge solar cell panels is problematic. Small area, no problem. You can get 22% efficiency. Once you make it into large area, the efficiency drops. So that's the problem. And only Japanese can do this because Japanese is very well known for their Six Sigma process. Yeah, US company cannot make it. Only Japanese company can show a good efficiency for large manufacturing. Okay, now so another problem with CIGS is we need to use indium and gallium. These two materials are considered quite rare and expensive. Because of that, people try to find a cheaper alternative, but also the same family as CIGS. So we have what we call as CZTS: copper, zinc, tin, sulfide, and selenium. So this is also a 4 or 5 elements semiconductors. Yeah. Now the good thing about this material is the band gaps can be tuned from 1 to 1.7 eV, depending on how you control the amount of sulfur and selenium, right? And the theoretical efficiency of this material is 30%. So this is very good. However, the best demonstrated lab based solar cell is 12.7% only. You see, there's a big difference between 30% to 12.7% efficiency. And actually, just a side note, the team behind the record efficiency of CZTS, one of them is Indonesian. And he's very famous. You guys may know him because especially if you guys take part in TOEFL, the physics Olympiads, you may know this person. Anybody wants to guess? No TOEFL contestant here, yeah. Okay. The person name is Dr. Oki Gunawan. He is one of the first students of Professor Surya who win the TOEFL gold medal, or I don't know what medal he won before, but he now works in IBM and he's part of the team that make this high efficiency solar cell. And I'm fortunate enough to know him personally, collaborate with him, and also co-publish with him. In fact, today he just sent me an email which I have not replied because he wants to meet. He wants to discuss more things. Yeah, sorry, I have to prepare my lecture for UI. I cannot entertain his email yet. Okay, so okay, that's a side note. So you guys should be proud. You know, Indonesian scientist is behind the highest efficiency solar cell in the world. So you see, this is Indonesian scientists are very good. You know, you should be inspired and try your best. Some of the best brain in the world is in Indonesia. It's up to you whether you want to use, how do you want to use it. Okay, the potential is huge. Okay, now coming back to solar cell. The problem with this material is there are too many defects in this material. To make it a short point is this is a defective material. And how can we reduce the defects is by substituting, changing the composition of copper, zinc, tin sulfide. If we look at the periodic table, how can we do that? We start with the main elements, copper, zinc, tin sulfide. We can replace copper with silver or lithium. We can replace zinc with cadmium, manganese, magnesium, barium. Tin we can replace with germanium. We can also dope this material with different elements. Okay. And my group have been doing this. So for each of these elements that I circle in blue, we have at least one publication. Yeah. So you can see actually material science is very easy to publish. You just change one element, do a study, publish one paper. Yeah. Of course, it's not easy. One paper will take a few months at least, or even a year to generate. Okay. And the method to fabricate this material in my lab, we don't need very high equipment. We don't need a sophisticated machine. We just need chemicals. So we use a solution base. We produce ink, okay? And then we spray this ink on a piece of substrate and then do a chemical buff deposition, also using a beaker. I'm sure you can find this in your lab, yeah, a beaker and a hot plate. And then the only vacuum base we use is sputtering. I'm sure you also have sputtering system. I think I remember I asked before, you have a sputtering system. And then the last contact is using a thermal evaporator with a mask. But my student is actually now getting more creative. They just use a brush, yeah, and they just paint using their hand, and they get even higher efficiency. So my student is also artist, yeah. They can also make a very good efficiency using their own hand. Okay. So by changing the composition of the casterite, we can change the defect property. And to cut the story short, our group managed to produce the highest efficiency of novel casterite in the world so far. Yeah, so copper, cadmium, tin sulfide, we managed to get almost 8% efficiency. Okay, so this is some of the activities in my group that I'd like to share with you, and this is an example of how you can use material science to solve the problem in solar cell. Okay, and actually be competitive with the world. I don't have the facility of IBM. I cannot beat their 13% efficiency. But what I can do is I can offer a alternative approach using different materials that shows lower defect density. And maybe all the big guys, right, they can pick up this research and use it in their lab to produce using a much more sophisticated equipment. So for university lab, right, what is our strength? Our strength is in innovation. Our strength is in our students. How can we beat big labs, IBM? They have their budget is probably 10 times our budget. How can we beat them, right? We can beat them by doing more innovation. Yeah, and I believe all of you also can do this. As long as you want to do it, you have the will to do it, you will find opportunity to be world class. Okay, so one of the example of the CZTS solar cell that our group made is semi-transparent CZTS solar cell. So this can be used on Windows, yeah. So our work is just accepted in Solar RRL. And then now I want to move on to the third generation of solar cell. So my discussion so far only deals with inorganic materials. In the third generation of solar cell, we start to use organic materials like polymers, small molecules, etc. In general, we have organic photovoltaic, we have dye-sensitized solar cell or perovskite, as well as organic inorganic hybrid solar cell. So organic photovoltaic also has similar configuration, similar architecture as silicon solar cell. You have P-type material, N-type material, but organic semiconductor, people call this donor materials. N-type semiconductor is called acceptor. And then it is also sandwiched by positive electrode and negative electrode. Okay. Okay. My animation doesn't work. Let me see. Oh, okay. Anyway, I probably cannot spend too much time explaining this. Okay, maybe in short, most of the solar cell that we discussed just now consists of layers, yeah, distinct layers, like kue lapis, like that. But in organic photovoltaic, instead of kue lapis, you have marmer cake, yeah, marble cake, okay, because you actually mix the P-type and N-type semiconductor into this kind of what we call bulk heterojunction. Yeah, so there is an interconnected pathway. So the P-type material is the white color here. It will conduct holes, and the black color materials is the N-type. It will conduct electrons. Okay, there is a reason why we need to do this, but I don't have time to go through it with you. Yeah. Okay. Now the problem with organic photovoltaic is this is made of polymers, right? This is made of plastic. And if you notice, plastic doesn't last long. Your plastic can change color from transparent to yellowish, right? This is what happened with organic photovoltaic because plastic absorbs UV, and this degrades the polymeric structure. Okay, so because of this, the overall lifetime of organic photovoltaic is low. If silicon can guarantee 20 to 25%, 20 to 25 years of lifetime on the rooftop, organic PV, the best organic PV, I think, can only guarantee up to 10 years, probably even 5 years. So the drive to replace silicon with this is quite low. Yeah, people don't see the need why they need to replace silicon with organic photovoltaic. Okay, so actually 5 to 10 years lifetime is already good enough. For those who have done this research, you will know that in the lab, the organic photovoltaic will degrade over a period of days without encapsulation. But those that is being manufactured has a encapsulation, like using this PN plus super barrier that will prevent the moisture to go in. Yeah, it will prevent is some kind of food packaging material. So nowadays we vacuum a lot of food to prevent moisture or oxygen to go in. We use similar type for organic photovoltaic. Yeah. Okay. Now, what is the benefit of using organic materials? Organic materials is good because it absorbs much better than inorganic. The absorption coefficient of organic materials is 100 times better than silicon. So silicon, so the thickness of organic photovoltaic is 100 times thinner than silicon. Because of this, within 100 nanometer, 200 nanometer thick of organic material absorb the same amount of light compared to the 100 micron thick silicon. Okay, so because of this, people are very excited about organic materials. They want to make good organic materials, and they can synthesize the organic materials. The problem with organic materials is the electron and hole mobilities are not as good as silicon, and the stability is poor. Now, can we combine the benefit of inorganic and organic materials? In inorganic materials, the benefit is it is high stability and long electron hole diffusion length or mobility. Organic materials has high absorption coefficient. So people try to do this. They combine both polymers as well as inorganic materials. But to be honest, this is not good enough, yeah, for a lot of reasons that I will not discuss here. Another class of good solar cell is dye-sensitized solar cell. Now, this material is very easy to make. Probably you can also do it in UI, yeah. I think Prof. Herman research last time is also in this area. So this dye-sensitized solar cell consists of a back electrode. Okay, so you start with the glass or the TCO material, and then you deposit a TiO2, titanium dioxide mesoporous structure, and then you immerse this into dye. Yeah, the dye also can be made from the dye of the fruit dye, natural dye, fruit dye like strawberry or beetroot. Yeah, and then you prepare another electrode, and then you sandwich these two, and then you inject an electrolyte. Okay, this is called a dye-sensitized structure. Okay, now the efficiency of a dye-sensitized solar cell is around 11% for since 1990s to 2012. So it's around 20 years. The efficiency is stagnant, 11%. People are quite desperate already. Then suddenly they found this material called perovskite. They replaced the dye with perovskite, and the efficiency jumped up. Now it's already 25%, as good as silicon. Yeah. So perovskite is made of organic, inorganic materials consisting of metal, ammonia, lead, iodine, bromine. Yeah. Sometimes they can also use chlorine. Yeah, which replace the dye in dye-sensitized solar cell. This material is amazing because they have good absorption coefficient, they have good band gap, and they also have very good electron and hole mobility. Yeah, because of this, a lot of research interest in this area. So this is the how organic perovskite solar cell looks like. Okay, I will not go into details. And both dye-sensitized solar cell and perovskite can be used also as a semi-transparent windows. And actually, we have to think of solar cell beyond silicon. Yeah, silicon is, if we want to do research, silicon solar cell research is almost done. Okay, because it's already go through manufacturing process. What we should think about is, can we deploy solar cells in non-conventional places? For example, as the window here on the this is installed in a bus stop, at the bus stop in Melbourne. Yeah, so if you got a chance to visit Melbourne, go to the city center, find this bus stop. All of these glasses are made of solar cell at the site. Yeah. Also, you can use it as a facade here, semi-transparent facade, or on the greenhouse. Yeah. Or you can also install it on the car. Okay. So in order to do this, you have to work with materials other than silicon. Okay, so one example is a perovskite solar cell that we work on in the lab. We managed to make a semi-transparent solar cell, okay, with a different types of imprinting technology. Okay, and the material that is good for solar cell can also be used to generate oxygen and hydrogen through an artificial photosynthesis process. So what we are trying to do is we try to mimic what the leaf can do very well, which is to convert CO2, yeah, carbon dioxide, sunlight, and water into sugar and oxygen, carbohydrate and oxygen, right? So there are many efforts going on in this area, and this is also something simple that you can do because the equipment that you need to do is just a potential start, electrochemical devices. All right. Okay. So as a summary, I think we have gone through all of this basic principle of photovoltaic material selection, 3 generation of solar cell. Okay. Maybe I would like to take this opportunity to check whether you are listening to my talk. So can you go to WooClap and try to answer the next question? Are you able to see the question? Basically, this is the question that I am posting. Can you see the question in my screen? Match the
We can see.
can see? Match the element with the type of solar cell it is used. So remember, I posed this question before, right? Which element is used in solar cell? So now on the left-hand side is the elements, on the right-hand side are the type of solar cell. So which element is used in which type of solar cell? Okay, the response is quite slow. Maybe this is a too long question. Yeah. Okay. So while waiting, okay, while waiting, maybe I will share a few more slides, advertisement slides. Okay. So can you see my slides now? Can you recognize the VIPs in this slides? Okay. So I'm sure you are familiar with the guest of honors in these slides. Okay. So this is before COVID, right? We got a chance to host Prof. Herman in NTU. So hopefully we will have a collaboration, more intimate collaboration between MSE and DTMM. Okay.
Hopefully, yeah.
Yes, yes. So if any of you are interested to take up scholarship, postgraduate scholarship in NTU, there are a lot of possibilities, yeah. So I'd just like to bring this attention to you. You can do a screenshot. You can take a photo of this. NTU is in the LPDP regular program. The call this year, I heard, will be open very soon, probably next month. Okay. probably it's too early for you, but you can plan ahead lah, right? What I want to share is probably also for Prof. Herman and also maybe for some of the staff here, we can provide a conditional acceptance letter. Okay, so for example, I think I helped one of your staff before to get this letter from NTU. So basically, if you meet our acceptance criteria, but you are waiting for LPDP scholarship, we can give you a piece of letter to say that we will accept you as our student if you secure the LPDP scholarship. Yeah. And then if you are more interested in NTU or Singapore-based scholarship, you can check out this SINGA scholarship. The problem with, okay, not the problem. The SINGA scholarship is meant for non-ASEAN students. But if you do your second degree or your master in other countries other than ASEAN, you can apply for PhD under this scholarship. So for example, now you do your S1 in UI, your S2 in Eropa, and then you want to come back to Singapore to do PhD, you can apply for this scholarship. Or your S2 you do in Taiwan, Korea, Japan, then you can come back to do PhD in NTU using this scholarship. Another scholarship is NTU Research Scholarship. This is a direct PhD program. No need to do master. Straight away go PhD. You can do that. This is the QR code to access this. You can take a look at the requirements. Okay, if you do not manage to secure scholarship, self-funding options for Master of Engineering or PhD are also available. And if you're interested, you can check with me or Prof. Herman. Actually, last time Prof. Herman is also did his PhD in Singapore, right? So you can find out more from him. Yeah. Okay, and now this is for postdocs. This is maybe relevant for lecturers or associate professor in UI. Yeah, Prof. Herman, maybe you can share this with your colleagues. This is a MRSS Visiting Researcher Scheme sponsored by MRS Singapore. So this one is for early and mid-career material scientists in Asia. They can visit NTU or NUS for a minimum of 3 months. The funding is $10,000. This $10,000, a lot, right? This $10,000 will cover your air ticket. Now we have more costs because you need to be quarantined in a 5-star hotel. So that will cost you another $2,000. But then after that, the rest is for your living expenses. Yeah. So if this application is open all year long, you can visit this sites, yeah, to check the details. The contact person in NTU is fortunately or unfortunately is me. Okay. So
okay.
yeah, so you know the meaning lah. Fortunately or unfortunately is me. Okay.
And
So in NUS is Prof. Ding Jun.
Yeah, magnetic material.
Yeah. Prof. Herman should know him. Okay. All right. So this is for your information. You can feel free to spread this around.
Yeah,
okay. So now we can come back to this. Can come back to the result of the question just now. Let me see. Okay. I think there are 20 of you already responded. Okay. The most frequent answer. Tellurium, cadmium telluride, that's correct. Cesium, perovskite, that's correct. Copper, CIGS, that's correct. Carbon, organic, that's correct. Silver, silicon solar cell, very good. You are listening to me, yeah, because I told you silver is in the top contact. Or some people also say silver is perovskite solar cell. Okay, I did not say that, but you are not wrong. Actually, we do use silver as one of the layers, yeah, but it's not that common. It's not that common. We use it for some other purpose because anyway, it's a long story. Not very common, but it is not wrong. Hydrogen in perovskite solar cell. Correct, because some of the component of the metal ammonia contains hydrogen. Yeah, but hydrogen is also used in amorphous silicon solar cell. and also in silicon actually. Why? Hydrogen is a very good dopant, passivating dopant. It can passivate the defects very well. I think in almost all type of solar cell you can find hydrogen. People are still wondering, what does this hydrogen do? Yeah, because it's so small, it can actually just go to passivate any defects, and it is quite electrically benign. Chlorine is used in perovskite, that's correct. Hydrogen in organic solar cell, this is also correct. Chlorine in amorphous silicon, I don't think so. Silver in amorphous silicon could be correct because it is used as a contact. Copper in perovskite solar cell, some, okay, not wrong, some of the perovskite solar cell has copper, but not the best efficiency one. Chlorine in organic solar cell, yes. Cesium in CIGS, no. Copper in silicon, no. Carbon in perovskite, yes. Carbon in amorphous, no. Hydrogen in amorphous, yes. Silver, CIGS, correct. Copper, okay. Anyway, let me show you what is the correct answer. Silver in silicon solar cell, copper in CIGS, chlorine in perovskite solar cell, carbon in organic solar cell, tellurium in CATL, cesium in perovskite, and hydrogen in amorphous silicon. Okay, so with that, I think I will close this session, and I'll still be happy to take up any questions if you have. I think it's pretty late also, but I'm happy to take questions if you have.
All right, I guess that's for the lecture from Professor Lydia. I think we still have probably 5 minutes.
5 minutes,
So
yeah.
I will take this opportunity to give probably any of you still have confusion or any inquiry regarding this lecture, please raise your hand and you can unmute and directly ask question to Professor Lydia.
Don't shy cat.
Oh, there already one who raised his hand. Okay, you can unmute, Baginda. You can unmute yourself.
Okay, hello, Prof. Actually, I want to ask, like, what is the proper way to respond to the changing nature around the solar cell, like panel? Like, how can we, like, have a constant temperature in solar system output, maybe? Like, how to respond to the nature?
You mean the temperature?
Yeah, the temperature.
You mean sometimes the hot heating, right? The heating effect of solar cell. There are many ways. One way is to use a cooling system. Some people use water at the backside of the silicon panels to cool down the heating effect.
Okay, thank you, Prof.
Okay, hope that answer your question, Baginda. The next question probably from Huzaifah Al-Hijri. Okay, you can unmute yourself.
Okay, thank you for your time, Professor. I would like to ask for your opinion. So basically there's basically like 2D materials are really quite the hot subject right now. And one of those 2D materials is the material silicene, which is basically the 2D structural allotropy of silicon itself. And from what I've read myself, silicene has good electrical properties similar to graphene. So what I would like to ask is, what is your opinion on the potential of silicene as a solar cell material? Thank you very
Cannot
much.
work. My opinion, it will not work because absorption coefficient of silicon is quite low. You need 100 micron of silicon to efficiently absorb photons. So silicene is one layer, one monolayer of 2D materials. So yes, it has the electron mobility may be very high, but it will not work as a solar cell. It may work for electrical devices. Yeah, it's good for nano electronics to replace your chip in your handphone.
Thank you very much for your answer, Professor.
Okay, thank you very much, Huzaifa. The next one.
Very good question. Very
From,
good question.
next one, probably from Fadian Ramadan. You can unmute.
Okay, thank you. Hello, Prof. My name is Fadian. I would like to ask that you mentioned earlier that the requirement of the semiconductor applied in solar cell is that the photon energy must be bigger than the band gap energy of the semiconductor materials. And thus it will also produce the excess energy, which is released in the form of heat. So my question is, does this heat will affect the performance of the solar cell material itself, or even the materials that form this solar cells device itself, especially in the long-term application? Thank you, Prof.
Okay, very good question. So heat can have different effects, right? I answer your second
I'm
question.
sorry, Prof. Lydia, the audio it's not clear,
Oh,
probably.
okay.
The
So,
microphone.
all right. So very good question. Maybe I address your second question first, whether this will affect the material stability, right? Fortunately not, right? Most of the phases of the materials will not change just because of the heating effect of solar cell. However, not because of this extra energy of the thermal excitation. However, if you expose solar cell at a prolonged time, at a long time outside, right? Then there's also a heating effect from the sun. This temperature gradient can go up to 70 degree. Yeah, so outside our temperature is 30 degree, 35 degrees C. But because the silicon absorb this heat and also trap the heat, the real temperature of your silicon panels on the on the rooftop can go up to 70 degrees and higher. This effect over a long period of time may change the efficiency of your solar cell. It's not that much for silicon. That's why silicon is very stable. For some materials, it may affect, for example, for organic photovoltaic. This is also one of the problem. They are not heat resistant, right? And also some of other materials, you can release the dopants when you increase this temperature in when you expose this to sunlight, yeah, but not really from the thermal excitation, but more for this prolonged exposure. But okay, this is actually a very good point, because imagine if your band gap is very low, right? Just now I mentioned your band gap should be as low as possible, right? But if your band gap is less than 1 eV, most of the photon absorbed will convert to the thermal energy. So material with a band gap of lower than 1 eV is actually a good thermoelectric material, not a good photo or solar cell material, photovoltaic materials, because the one that is converted to heat is much higher than the electron. Okay, but this is a very good question. So actually, the best solar cell materials, the lowest band gap that you can go is 1 eV. Lower than 1 eV, you better try to do it for thermoelectric. Okay?
Okay, thank you, Prof.
Very good question. Okay, any other questions?
I think we have our last question from Benedictus. You can try to unmute yourself and ask directly.
Okay, thank you for your interesting presentation, Professor Lydia Wong. Actually, I have a question that maybe have been presented by you, but I still have a confusion. As we know that materials for making solar cell technologies can be made from single phase materials, such as silicon, either amorphous or crystalline, but we can also engineer material for solar cell technologies in the hybrid form, such as compounds or alloys. But I am still wondering to know the latter. What are the guiding principles to make compounds or alloys materials for making solar cells? or other ways, how can we choose the materials two or material tier to make a compound? Thank you.
Okay, so if you really want to know, I think you need to do research in this area. But to give you the short answer, right? I told you the starting point already. Filter the material or select the materials with a band gap of 1.1 EV to, let's say, 2 EV, because beyond that is not so good. Yeah, so band gap first. Once you have the band gap, the second one is absorption coefficient. It has to absorb enough energy within a thin materials, right? And then the third one is good electron and hole mobility. So at least these three principles, if you can fulfill this, then you can try to use it for solar cell. Yeah. Now, if you choose from, so this you can only do for materials that is already synthesized, that people already report. People already report what is the electron hole mobility, what is the band gap, then you can choose the material and use it, right? Now, the question is, if you go back to the periodic table, how many combinations of compounds can you derive from this periodic table? Millions, right? Millions. How can you predict? Now, this is the beauty of machine learning, and this is what actually many of us are trying to do in NTU. Can we simulate, compute? You combine material A and B, calculate what is the orbital, what is the band gap. Yeah, if you go back to solid state physics, you have two atoms, get them together. What is the minimum distance? What is the curvature of the valence band, measure the band gap. This can be calculated. Computational material science. I'm not sure whether you have this in UI, yeah? Simulation, computation material science. You can predict the band gap, you can predict the absorption coefficient, and give this prediction to the experimentalists to synthesize the materials. And we want to do this in a very fast way using artificial intelligence and high throughput synthesis, and with the help of machine learning. Yeah, so this is the next question that we want to do in the next 10 or 20 years. I hope my group will have some success, and then in a few years time report back to UI and share our results. Okay, thank you for the question.
Okay, thank you very much for all the questions and for the answer from Professor Lydia. I guess that's sums it up for today's lecture. We have a very nice and very enthusiastic students here. So, and I hope all of you can success later for the study in, for example, this solar cells materials in the derivation, and probably you can make a new compound that can work as a solar cells materials. Thank you very much. I guess we can call it a day for this lecture. And perhaps before we close,
yeah,
yes,
please.
Yes, before we close this session, I hope we can take a picture together. So probably all of you can turn on the camera so that I can take a picture together before we close this session. Since we have probably 3 pages, so I will take the photo 3 times. Okay. Okay, I think most of you already got your camera on. Okay, 1, 2, 3. Okay, for the next page. 1, 2, 3. Okay, for the last page. 1, 2, 3. Okay, I guess that's all. Thank you very much for all the students who participates in this session, and thank you very much for Prof. Lydia Wong. I hope you can have more success in the derivation of these materials for solar cell, and then we can collaborate more between UI, Universitas Indonesia, especially Department of Metallurgy and Materials, and Material Science and Engineering in NTU in the next future. Thank you very much for all the participants. I will close this session by saying Alhamdulillah, selamat sore, selamat beraktivitas.
Okay,
Thank you very much.
Thank you so much everyone. Selamat berbuka puasa.
Thank you Bu Lydia.
Iya, Pak Herman.
Dan seluruh student dan juga dosen yang hadir di sini, Pak Bambang Priyono dan semuanya atas partisipasinya. Ya.
Thank you, Prof.
Berjumpa kembali. Insya Allah nanti kita akan mengadakan kegiatan seperti ini lagi.
Ya, amin. Semoga bisa cepat ketemu ya, face to face.
Salam buat keluarga Bu Lydia di rumah.
Sama-sama Pak Herman, sama-sama. Oke, mari.
Ya.